Hello. So today in our class, we're going to discuss about the sorry for the delay. Today we are going to discuss about the load characteristics of a series, shunt, and compound DC generators. Now, as we all know that these DC machines can be magnetized in two different ways. They can be magnetized either in a self-excitation manner or in a separately excitation manner. So the separately excitation consists of a separate DC source, a battery, etc. While the self excitation consists of series excitation, shunt excitation, and compound excitation. Now, series excitation, as we all know, is if the excitation coil or the field coil is connected in series with the armature. Shunt excitation means if the field coils are connected in parallel with the armature, and compound excitation means both series and shunt coils are present alongside with the armature coil. Now, in the separately excited DC generator, we can see that here the another field is applied, which is a DC source applied to this DC generator, where the output terminal is connected to a load. Here we can see for the ideal condition when there is no load or it is an open circuit, the ideal characteristics should be a straight line, which is the normal characteristics of a DC waveform or DC wave, right? So this straight line represents the characteristics of an ideal thing or ideal DC machine which is not connected to a load. So whenever a load is connected to this armature or alongside this armature in the load side, there will be a voltage drop across the armature. So here there will be a voltage drop which is IARA, right? So this is the IARA which is dropping, and EA is the resultant output voltage. Now due to armature reaction, this voltage again drops to a certain level, and this VT is the actual output voltage of the DC generator in case it is separately excited. Now here we can see that there is also an increase in current, and this increase in current is due to the application of load. As load is applied, the actual current gets increased and there is a voltage drop across the load, which is called the ohmic drop, right? So what are the advantages of this separately excited DC generator? First of all, the voltage of the exciting current is entirely independent of the load current in the armature. Thus, the machine may work satisfactorily over a range of voltages extending from 0 to maximum, which is which the machine can generate. However, practical voltage range during operation is limited to a certain level. Now coming to the self-excited generators. Now here we can see the self-excited generator. Now we all are familiar with the circuit diagram of this DC self-excited generators. Now let's see that the field or the excitation field is entirely dependent on the number of turns that is being put into the field or put into the shunt field, right? So we can see that this is the ideal condition. This is the ideal condition for the mm, generator. This is the actual voltage that should be supplied if no load is applied to it or there is an open circuit. But this we can see with the application of load there is a consistent drop in the output voltage Vt. Now this drop continues up to a certain limit. This drop continues up to a certain limit which increases the amount of current. Now at a certain stage, this is the critical stage, after this stage the voltage again drops as well as the current. So this kind of generators can allow a load to a certain limit. After the load is being excited or current is more implied to it, the voltage will drop along with the current and will come to a rest. So the number of turns in the field winding is large. Field winding resistance is higher, and the rated field current is lower that of other types or other types of machines that we have seen earlier. The shunt generator has a more drooping characteristics than separately excited generator. This is because the machine is loaded, the terminal voltage decreases. This in turn also decreases the field current, which reduces the generated EMF, causing a larger voltage drop across the terminal voltage. Then that would be observed in the case of separately excited generators. Now coming to the next generator, which is self-excited generator or self-excited series generator. Here the characteristics of this generator seems very simple because with the increase of load, the voltage also increases, and this is the limit where it starts to drop or the voltage starts to drop. This is called the critical voltage, or sorry, uh, yes, the critical voltage. So whenever this achieves the critical voltage, or this machine achieves the critical voltage, there will be a certain drop in the voltage and will rest in zero, or the voltage drop will continue until it becomes zero. So in this case also the field winding has only a few turns and a low resistance. The rated series current is equal to the rated armature value. Series windings of compound machines have been smaller number of turns. Now the series generator characteristics are quite different to that of the two types of generators that we have seen earlier. Mm, This is because the field flux increases with increasing load current. Hence, the terminal voltage increases as well, that we have already seen. This goes until the voltage reaches a critical value, and the critical load current value has reached to a certain limit. So this is where the critical current value should reach, right? This is where the critical current value should reach, and at this critical current value the voltage will start to drop until and unless it reaches zero, and this happens due to the armature reaction in the self-excited series generator. Now coming to the next machine, which is a compound generator. So the characteristics is quite confusing, as we can see that these characteristics has three sections, although machine cannot have three characteristics at the same time. So these three characteristics has its own point of application where these characteristics should be applied. This will be shown in the next slide, but let's talk about the generator first, how the generator works. So the compound generator has both series and shunt field windings. The short shunt connection, where the shunt field is connected in parallel to the armature, right? So we all know about the short shunt and long shunt combinations of the shunt generators. Nextly, if the shunt field winding is connected in parallel to the load, it is called a long shunt connection. The polarity of the series field is also important. The series winding may be connected such that it may strengthen the field shunt field. This is additive compounding. This process is called additive compounding. Or it may weaken the shunt field, which is called the subtractive or deductive compounding. In practice, subtractive compounding is used very exponentially, or it is used more frequently. Now, coming to the next section. Now, additive compounding machine characteristics is shown over here, where the additive compounding works, or the flat compounding works, and the under compounding or the subtractive compounding works. Now, here the additive compounding to work, the additive compound machine characteristics may further be classified according to the strength. Now, this additive compounding um, relies on the field strength, or is quite dependent on the field strength or the series field strength. Now, if the number of turns in the series field winding has more number of turns, or sufficient number of turns, then this is called over compounding. And if this over compounding happens, then this will follow the state A characteristics of the over compounding in case of compound generators. Now, if the number of turns is just adequate to compensate the voltage drop due to the armature circuit resistance, then it will show a flat curve, which is near ideal condition, flat curve, which is just compensating the armature circuit resistance. This will be represented by this stage B, or the situation B. And if the field windings in the series is weaker and the armature resistance is much higher than that of the field winding, then this case C, or under compounding, happens. So the if the rated current to the to the machine is represented by this dotted line, and the rated voltage is represented by this dotted line, so we can see that if it will continue to be in its ideal condition if only the case B is satisfied. Otherwise, it will either follow the over compounding method, over compounding characteristics, or the under compounding characteristics if there is lesser or more number of coils in the series field. So these are the characteristics of DC generators, different types of DC generators. We'll talk about the load characteristics of DC motors in the next class.